Okay, so this is going to be a quick-ish video to basically go through and show you some of the tools that you can use in Excel to help you explore some data sets, and particularly looking at correlations between different parameters in a data set. So this is an example from of a geochemistry data set where we have a bunch of samples, and for each sample there are a bunch of different parameters. So we've got location of the samples, but we have all of these different measurements that have been made. If I just scroll across here, you can see that there are lots of different elemental compositions here. We've got some trace element compositions, some mineralogy, and we've got a whole bunch of other leachate data as well, which we might want to play with and explore and see if we can find some trends between different parameters. Okay, so I'm just going to go through the process of doing that. But first of all, it's quite a large spreadsheet. This is quite hard to kind of constantly be switching around backwards and forwards. So one feature that's quite useful in Excel is if you want to basically keep the headers of each row of each column of data visible as you scroll around, and maybe also the sample numbers, you might want to keep those visible. You can pick a cell in the spreadsheet which has got which basically as a point where you want to split the screen up into different parts. So here I'm just underneath the row that has got all of the column headers in, and just after the column that has all of the sample data in, or sample names here. And if I just go to view, I can choose this freeze panes thing up here. So I'll click on that and then freeze the panes, and you might be able to see that there are slightly thicker grey lines have appeared in between column A and B and row 3 and 4 here. So as I scroll around the spreadsheet, you can see that it keeps those rows fixed in place, so it's easier to navigate around the spreadsheet. So I recommend you do that. It makes your life a little bit easier. So looking now at how we might, kind of the things we might want to do to explore the data, I might be interested in seeing if there are some correlations between some data sets, some of these different parameters. So I might, for instance, pick, see if there's a relationship between the silicon oxide concentration and maybe the calcium content of the sediment. I mean, who knows, that might be quite interesting. So to do that, you can highlight the data, insert a chart, a nice XY chart there, and just for a quick look at the data, just using the default chart like that, not bothering with any kind of labels on it, I can kind of see that there doesn't seem to be much of a correlation going on there at all. If I want to change what I'm looking at, you can go onto the edge of these highlighted blocks of data where the chart is looking for and move them around. Now, you can move them around like that. But if I wanted to change the silicon one, you see I can't grab that and move it. So to be able to do that, you just have to make sure that you've got the data selected, and then I can move this to wherever I want. So I might want to look at, see if there's any variation between iron oxide and magnesium oxide, and you can see that I get a nice correlation here. So that might be something I might want to look at in more detail. I might make a note in my notebook about that's an interesting correlation. I'll come back to that later. And you can carry on. You can look through a bunch of different things, see if they correlate with each other, and so on. Okay, so that's a very useful tool. But you can see in this data file we have many different things we might want to plot and look at. Okay, so doing that manually for every possible combination of parameters would take forever. So we're going to go through a way of maybe doing this a little bit more intelligently and using some of the features of Excel which allow us to basically to check correlations between data and do it basically all in one go and see every possible correlation. So I guess the first thing to point out is the thing that we're actually going to be looking at here. So if I just go back to looking at between, got to select the data, of course, because I forget that kind of thing. Looking between iron and magnesium. So magnesium is on the y-axis, iron is on the x-axis here. So I'm not bothering to label anything because I'm just using it as a quick kind of check. So if we wanted to check how good this correlation between these two variables is, the way you might be familiar with that is we kind of click on the data series here. We might add a trend line, get a lovely nice trend line here, and then we could maybe click on the trend line and format it, and then maybe display the R squared on the old thing there. See if I can make that text options. Maybe if I just go up here and make that bigger. Okay, so hopefully you can see we've got a nice correlation coefficient in R squared of 0.88. So what that means is that 88% of the variability in one of the variables can be used to explain the variability in the other variable. So that suggests that there's kind of 12% of variability that cannot be explained by the other variable. So that's seemingly quite a good correlation. We could go through and do that for every possible thing, every possible pair of parameters. That, of course, would take forever if we did it this way. There is a formula which allows you to calculate the correlation coefficient. I'll just pop an example up in this cell up here. So, for instance, I wanted to know the correlation coefficient between iron and magnesium. I could use this Excel function equals correl, okay, and then I just add in the data that I want to compare. So iron and magnesium, and that gives me this lovely number here. I'll just give that maybe some more bigness. Ooh, bigness, so you can't see it there. So you can see that's 0.9391. Now that's not the same number as this one, and that's because this is calculating R. This is R squared. So if I could take that number and square it, I would get, so you can see that, I get basically the same as we would get in the old graph way of doing it. So that's, again, great, and you could maybe find some way of automatically kind of doing the correlation between every possible pair using that formula. And again, that might be quite complicated to do everyone. It'd be very easy to do the correlation between each kind of adjacent set of data, but we really want to get every possible combination. So silicon correlated against everything, aluminium correlated against everything, one by one. So we're going to go through and see, use a function of Excel that will be able to create a nice array of results that that provide us with this correlation coefficient here. So the R squared gives us basically the fraction of variability in one variable that can be used to explain the variability in the other. So that's useful in terms of determining how good correlations are. R on its own is useful because sometimes if you had a negative correlation, so if the slope went the other way, if you used R squared, that would still give you a positive number because a negative type of negative is a positive. So the R value preserves some knowledge about the slope or the whether it's a positive or negative correlation between the two variables. Okay, so this is the one that we're going to look at. It's very easy to calculate one from the other just using squared or square roots. Okay, so I'll just delete this chart because that's going to be in our way. And the feature that we're going to use is going to use part of the Analysis ToolPak. So if you go to Data on the your menu up here. There might be over in this region of the toolbar here something that says Analysis ToolPak or Data Analysis, and you see it's not visible on my toolbar because I haven't activated that plugin to Excel. So to activate that, you go to File, go down to Options, and then head to Add-ins. Okay, this lists all of the add-ins that are available for my version of Excel, and the ones that you want to be make sure that you have are Analysis ToolPak. Okay, it should be available to most of you. And then basically to activate that, you go to Manage Excel Add-ins at the bottom, make sure it's on Excel Add-ins, click Go, and then just make sure that Analysis ToolPak is selected, click OK, and you can see that we now have this option of data analysis over here. Okay, so just to go through how that works, or how to make use of this. What this has is there are a number of, if we just open it up, there are a number of, I can't make that bigger, number of basically statistical things that can be done with this. We can do histograms. We can compare kind of two samples to see if they're the same or different. We can see if things vary. We can do Fourier analysis, which is apparently in Excel. But the one that we're going to be looking at now is correlation. Okay, so you can select correlation, click OK, and then this just gives you a window which you can basically input your data and say where you want the output. So before we do this though, all of the data that we give it has to be in a continuous block of variables. So if we just cancel that, if we look at the way that our data are arranged, we can see that we basically don't have any, there's a gap in between our headers and our data, okay, and the data analysis requires there to either be no headers or the headers to be in the first row, so we can't really have a gap here. And there are also some gaps in the data over here. I'll just get rid of this extra bonus little window over here. Okay, so first step would be to basically make sure that our headers are immediately above our sample data. So you could just delete this row here, but all I'm going to do is I'm just going to copy everything across, so I can basically see we have some. So I basically have repeated the header row so it appears immediately above the data, or you could have done it the other way. And I'm just going to go through and quickly just delete all of this space that's not being kind of used in between our lovely data sets here. So I'm going to delete that, so that kind of closes everything up. And let's close stuff up over here. Delete. Okay, and I think I'll leave it there. So I'll just look at this mineralogy data. So these are the percentage of mineral in our sample, and the X-ray fluorescence chemistry data. So major elements and minor elements. Okay. So what we're going to do is just go back to that data analysis. Okay, click correlation, click OK. And then we're going to select the data that we want to, I guess, first analyze. We can basically, I'm just going to use the mouse keys. Just click around. Okay, so that selected all of that, and that selected all of that. So I've just used the Control, Shift, and the arrow keys to do that selection rather than messing around with the mouse. So those are the data that we want to analyze, compare all of the possible correlation coefficients. Our data are grouped by columns, okay, so that each kind of data set is in a new column, not a row. We have labels in the first row, that's there. And we could click a cell in our why is it doing? Oh, I would have to select that. We could select a cell where the data would then appear in this worksheet or the output as an array. But I'm just going to put that in a new worksheet and give it a name. I'm going to call it correlation or correl. Okay. And I'm just going to hit OK. No, I forgot. Yes. So if you're going to do any kind of, I guess, mathematical correlation analysis, it can only deal with numeric values. You can't give it words. Okay, it gets confused. So somewhere in all of these data, there is one of these numbers is not a number; it's some text. Okay, so I'll have to go and find that, and I think I can remember that in the iodine data, there we go. Somebody decided that it would say that one of the data was not detected. So I'm just going to cancel that, and delete that horrible data point. Okay. Now we can go back and do the data analysis again. Correlation. Okay. It's remembered all of the settings from last time, which is kind of handy. So if I click OK now, it's chugged away, and you can see that we've got a new worksheet here, and we now have for every parameter. Okay, we have the correlation with every other parameter. Okay, and you can see some of these are negative correlations. So you can see that when silicon oxide is high, magnesium oxide is low. And we've got positive correlations. This one here, we've got aluminium oxide is high, magnesium oxide is high. Okay, so this is quite useful. We could maybe use some conditional formatting now. So if we basically highlight everything, we might be able to say go to home and conditional formatting, and we could maybe use some color scales. I do like color scales, and we could maybe use this. So this shows us where we've got nice big positive correlations. It's highlighted things in green. We've got big negative correlations. It's highlighted them in red. Okay, so where the color is more stronger, we've got a stronger correlation. So that's kind of quite a nice way of looking at the data, but we might want to think about this a little bit more rigorously in terms of, what is the cutoff for us to consider a correlation between one data set and another data set? Is that useful or not, or is that kind of correlation occurred by chance? So basically, is this correlation here, positive correlation of maybe 0.48, is that real, or is that just kind of random noise in the data that happened to give a positive correlation? Okay, so there are two ways of thinking about this. So we could go through for each of these correlations, and we could try and calculate what's called a p-value, which is the probability that that particular correlation coefficient has occurred by chance. So we could approach it that way, or we could look at it in a slightly different way and say, what is the threshold above which a correlation coefficient like this can be considered robust or statistically significant? And that's what I'm just going to go through now. So I'm just going to bring across a kind of a website here, which I found this useful information from. So this is I guess this is excelmastersseries.com 2014-05 Pearson correlation R critical and P HTML. I don't expect you to remember that. Basically, if you Google Pearson correlation critical value, you will come up with websites like this one, which allow you, or basically show you the formula from which you can calculate a critical R value, and that's kind of given by this formula here. This is a very useful website I found, so thank you whoever did that. That was pretty good. Like it. So the important things to note is that the critical value is basically a function of the student's t distribution. It's this alpha in here is the confidence interval by which we're wanting to assess our data. So if we want to be 95% sure or 99% sure, we would adjust this alpha value here to basically 1 minus that percentage. So if I'm interested in correlation coefficients that are significant at the 95% level, I would set this to 0.05. Okay. The degrees of freedom here, because our basically our correlation models, or that we're basically our best fit lines we're putting through these data to calculate these correlation coefficients, because that's of the form y equals mx plus c. Okay, so that's got a gradient and an intercept. So there are two basically variables in our model. So our number of degrees of freedom are the number of data points we have minus 2. Okay, so that basically the number of data points we have and the confidence interval are the only things which really determine our critical R, which means we can calculate one value for the critical R and then apply that to all of our data. Okay, so I'm just gonna go through that now, and I guess to help me, I will copy this formula. I guess I could actually just copy the formula from Excel that they've used for Excel down here. Let's do that. Aha, win for me. And then down here, I'm just going to say what the my R critical, and I'm going to say that is going to equal whatever I type into this cell here, which will be this formula here. So you can see we've got the inverse student's t distribution, 1 minus alpha, so that's working out at the 95% confidence interval divided by 2. Degrees of freedom, I've got 12 data points for each of my data sets, except iodine where there was some missing data, but I just have to make a note in my notebook that the correlation coefficients for iodine need a higher significance, or need a higher R to R squared or R to be significant. Put another 12 in there, and other degrees of freedom is there. I can hit enter, and that gives me a value of 0.575938. So effectively, these numbers have to be greater than these numbers. Okay. Now, I could use another conditional formula conditional formatting thing to do that, but I just need to be a little bit careful because the I don't just want to highlight numbers which are greater than 0.75 because our negative correlations are also significant. So you see the magnitude of some of these negative correlations is greater than our guy down here. So I'll just go back to conditional formatting, go to clear all the rules, sheet all gone. I'm going to highlight all of the lovely data. Yum, yum, yum. We all like data. And then I will go to conditional formatting, highlight cell rules. I'm going to ask for some more rules. Okay, so there are different rules. We can basically highlight cells that are greater than, equal to, the same. We can only highlight the largest or the smallest. It's a very useful way of searching through big data sets like this. But I'm going to use a formula. So I can make up my own rule, because when you're a grown-up, you can make your own rules, which is pretty cool. And my formula is going to be, I want the absolute value of, or the absolute magnitude of the data in this array. So I'm going to click first value. I'm going to remove the dollar signs because I want it to basically go through all of these data, not just look at the first one. And I'm going to say, I don't just want the value of that, I want, let's try abs. So that gives me the absolute magnitude. So if it's negative, it'll give me a positive number. And I say if that is greater than the number at the bottom of our spreadsheet down here, I'm going to leave the dollar signs in because I always want it to refer to that cell there. I'm going to then ask it to format that cell in a particular way. So I'll maybe make the fill. I might make it fill up with, everyone likes purple, right? Let's have purple. And click OK, and click OK. And annoyingly, that hasn't worked. Why has that not worked? And we'll go through and highlight this again. Maybe it's because I started at the bottom. Conditional formatting, clear rules from the entire sheet. Conditional formatting, highlight cells rules, more rules. Use formula. Is it going to be if that one, if the absolute value of that one is greater than sorry, click down here, format set to be purple, okay, and you can see now that I've basically got an array here which has highlighted all of the possible relationships that are effectively just worth looking at. So all of the stuff that's in white background is not a significant correlation. So I can look through these and say, actually, it's probably worth me looking at aluminium to iron and aluminium to magnesium to see if those correlations are interesting or not. All of the other ones, the correlations will not be interesting because they are not significant and they are just random noise in the dataset. So this is kind of like a first step. It should help you kind of go through your data and save you some time in identifying which data are interesting, which data are not interesting. You might want to do it for all of the data, not just the elemental compositions, silicon, iron, the major elements here, the minor elements, the mineralogy, but you might want to also include some of the organic geochemistry data, the sediment grain sizes, the positions, so the water depth or the geographical distribution of the samples. If you want to use the depth, you're going to have to convert this text value of 18m into the number 18. Now, hopefully, this has just shown you some useful ways which we can use some of the simple tools in Excel to really start to explore a data set and find things which are interesting. Okay, right. Let's stop that recording. Stop.